V equals I multiplied by R. It's often known as Ohm's law. It says that when there's a difference in electric potential and a path is supplied, charge is going to want to move from higher potential to lower potential. That movement is represented by the blue I because current is how much charge is flowing per unit time. But it's one thing for the charge to flow, it's another thing to consider, well, does it encounter any resistance during that flow? And that's what the red R is. So I'm going to pretend that we have a battery that's supplying some potential difference. So often by convention, you have two lines. The longer line will represent the positive terminal of the battery, and the smaller line will represent the negative terminal. And I'm going to say that I've got some sort of resistance that I'm going to call R1, and at some other time, I'm going to have another resistance R2. And so what I'm going to do is I'm going to wire things up here. I'm going to grab some wire and I'm going to make some connections. And here's the thing, when you see the wire, unless you're told otherwise, assume that this is an ideal wire that doesn't offer resistance to the flow of charge. One thing quickly about the flow of charge. We knew about electricity and started to develop a formalism for how to explain electricity before we actually discovered the electron. The electron was discovered in 1897. So when you see electricity and magnetism described in textbooks, a lot of that formalism was started to develop before we actually discovered the electron. So before we discovered the electron and realized that it was actually the movement of electrons that was the current in circuits, it was assumed that there was a what's called conventional current where positive charge moves from positive terminal to negative terminal. The only difference, as it turns out, is just the direction. All of the physics remains the same, and that's why we've stuck with the original formalism and nomenclature for electricity and magnetism. But just know that when I talk about charge flowing, I am talking about what the textbooks are talking about, and that is the conventional current. So I assume that a positive charge is flowing from higher potential to lower potential. But no, in real life, it's really electrons are moving. And you can imagine that atoms and molecules are in materials, and based on the bonds, some bonds allow for electrons to move more than others. So you can imagine materials where the bond structure is such that electrons can more freely move is going to make for a better conducting material. But for now, let's assume that this is a material where there's this completely free motion of charge. And again, I'm going to go back to charge now. So when I say charge, I'm going to talk about a positive charge flowing from positive terminal to negative terminal. We're going to assume the wire offers no resistance. If you look at the Ohm's law relationship, V equals IR, if no resistance is offered up to the flow of charge, there's going to be no change in the potential V. Okay, now the resistors do offer resistance by definition. Okay, and so what's going to happen is that if there's a potential difference, and a very common battery size would be, say, 9 volts. So let's say we have a 9-volt battery. That means that there's a 9-volt potential difference between the positive and negative terminal. Okay, what this means then is that if we provide a path, and by wiring up this circuit, we now have a path for the charge, the path wants to go from the higher potential back down to the lower potential, from higher electric potential energy to lower electric potential energy. This is no different than with gravity. If you raise something higher and higher, it has higher gravitational potential energy, and eventually, if given a path, wants to go back lower and lower, having lower and lower gravitational potential energy, and therefore that gravitational potential energy is transitioned into kinetic energy, the energy of motion. So if you can imagine a potential difference is established by a battery, and you have charge provided a path that wants to move, that movement means there is current. So if you can imagine going from the positive to the negative terminal, there is a current that is moving through this circuit, and it's going in the direction from positive to negative. So that blue is the current I. And so as the charge is moving, when it's just going through wire, the voltage is remaining the same. But if it hits resistors, there's going to be voltage drops. And again, this is in accordance with Ohm's law. So here we go. Let's say that we start at the positive terminal. And again, it's really electrons that are moving. And even more technically speaking, the electrons would actually be moving from the negative terminal to the positive terminal, because negative charges repel each other. And so the electrons want to get away from the negative terminal and try to go towards a location where there's a deficit of electrons, i.e. positive. But again, we're going to use conventional current. We're going to assume there's a positive charge at the positive terminal. It's at 9 volts. Remember, if given a path, it wants to get back to lower potential. So it wants to get back home to 0 volts. And so it starts going down the wire. And since the wire offers no resistance in the ideal case, we're going to assume that there's no change in potential. So for example, right here is still going to be 9 volts. Right here is still going to be 9 volts. And right here is still going to be 9 volts. However, once the charge starts to encounter resistance from resistor 1, there's going to be our first voltage drop. And I'm going to say that V1 is equal to the current I, and the I is the same through the entire circuit, so the same through both resistors, multiplied by whatever resistance R1 is, okay? And so now there's a voltage drop. There's something right here that's less than 9 volts. And it remains the same here, and here, and here, and here, and here, and here. Because remember, the wire does not offer resistance, so we say the voltage is the same throughout the wire. But now we encounter another resistor, resistor 2. And so for resistor 2, we're going to say that there's a second voltage drop, V2, and that's equal, the current's still the same, but now we have some resistor 2. And so that second voltage drop happens, and then we just have wire again. So it's going to be the same here, 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 and here. And by the way, if it's a 9-volt difference, then if it was 9 volts, the positive terminal right here is 0 volts. Okay? So we know that the charge starting at the positive terminal had to eventually go from 9 volts down to 0 volts. And to do so, it went through 2 voltage drops. It went through a voltage drop across the first resistor and a voltage drop across the second resistor. And the total voltage drop, not surprisingly, should equal the voltage supplied by the battery. And by the way, it doesn't have to be a battery. It can be any sort of power source that provides a potential difference. And so at the end of the day, the total V for this circuit, I'll call it V total, is going to be equal to V1 plus V2, where V1 is the voltage drop across the first resistor and V2 is the voltage drop across the second resistor, which is to say I R1 plus I R2. And it turns out, you see that the current, sees both of those terms. You could actually factor that out and say I R1 plus R2. And that would be the notion of the equivalent resistance of the circuit. As far as the battery sees, it's just a single resistor that is the combination of resistor 1 and resistor 2. But that's a story for another day. The key here is that if a potential difference is supplied by something like a battery, then charge, if given a path, is going to try to go from higher potential to lower potential. And so when going from higher potential to lower potential, there is a voltage drop when a resistance is encountered. And so if you look at the relationship of Ohm's law, V equals IR, there's some different ways in which you can think about how a change in one can change the other. So for instance, if I kept the same battery, a 9-volt battery, but I decided I wanted to put in a lot more resistance, then that red R term gets bigger. But if I'm going to keep the green voltage term 9 volts the same on the left, then if my R gets bigger, that means my current gets smaller. And this should kind of make sense. If the circuit offers a lot more resistance, you're not going to have as much flow. And if you don't have as much flow of charge, it means your current goes down. However, you could go the other direction. For a 9-volt battery, let's say maybe you took one of those resistors away and the net resistance went down. If the net resistance goes down, there's not as much resistance to flow, which means there's more flow, which means the current goes up. So I'm going to make one more connection back to gravity. Again, think of like a mountain. A mountain has higher gravitational potential energy at the top. And then if you're given a path down the mountain, a mass is going to move down that mountain and gain kinetic energy as the gravitational potential energy turns into kinetic energy. And it's one thing to go down a smooth side of the mountain versus going down a very rough, rocky, lots of friction side of the mountain. You can imagine the velocity in the latter case would not be as much because more obstacles are encountered as you try to get back down the mountain. And it's a similar thing with electricity. You can think of a potential difference as a mountain, and you can think of a charge as being at the top of the mountain and wanting to get back down to the bottom. And if it's given a path, then it's going to take that path. And when it takes that path, it means we have a flow of charge, which means we have current. But if there's lots of resistance along that path, the current flow is not going to be as much. But if there's less resistance along that path, the current flow is going to be more. So one last time, this is the concept of Ohm's law. V equals IR. When a potential difference is provided and a path is provided, you're going to have a flow of charge. And that flow of charge may or may not counter resistance. The more resistance it encounters, the more the flow is impeded. The less resistance it encounters, the more flow that you have.